Have you ever wondered how your computer decides which applications get to use its processing power and when? That's CPU scheduling at work. It's the unseen conductor of your computer's symphony of operations, determining which process takes the spotlight and when. It's a critical part of an operating system, efficiently managing system resources and optimizing performance. From streaming videos to running complex calculations, everything hinges on this intricate dance of processes. So let's dive into the world of CPU scheduling and see how it keeps our computers running smoothly. First, let's understand the objectives of CPU scheduling. These goals are what guide the design and implementation of scheduling algorithms, striving to make the most efficient and fair use of system resources. Objective number 1 is maximizing CPU utilization. The CPU, or Central Processing Unit, is the brain of the computer. It's where all the computation happens, and it's a precious resource. The aim here is to keep the CPU as busy as possible, executing processes without idle time. Think of it like a chef in a busy restaurant kitchen. The more orders they can prepare, the better for the restaurant's productivity. The second objective is minimizing turnaround time. This is the total time taken for a process to complete its execution from the moment it was submitted to the moment it's terminated. Imagine you're ordering a pizza. The turnaround time is the moment from placing the order to when you receive your piping hot pizza. Naturally, the shorter this time, the happier you are. The same goes for processes in a CPU. Next, we have minimizing response time. This is the time it takes for a process to start responding to user input or system events. Let's say you're playing a video game. The time it takes for your character to jump after you press the button is the response time. The faster the response, the smoother your gaming experience. Last but not least, we have the objective of fairness. This ensures that all processes get a fair share of CPU time and that no single process hogs the CPU. It's like ensuring that everyone gets a turn on the swings at the playground. If one kid hogs the swing all day, it's not fair to the others waiting their turn. These objectives guide the design of CPU scheduling algorithms to ensure efficient and fair use of system resources. Remember, achieving these objectives is a balancing act. Different systems and workloads may prioritize these objectives differently, but the ultimate goal is always to optimize system performance and resource utilization. Now let's talk about the different scheduling algorithms that help achieve these objectives. First up, we have the first come, first served, or FCFS scheduling algorithm. As the name suggests, it works just like standing in a queue for your morning coffee. The first process to arrive gets served first. Simple, isn't it? But here's the catch. It can result in long average waiting times, especially for long-running processes. Next in line is the shortest job next, or SJN, also known as the shortest job first, or SJF. This algorithm selects the process with the shortest expected CPU burst time. It's like the barista serving the quickest order first. However, it requires knowledge of the burst times, which may not always be available. Then we have priority scheduling. This algorithm assigns priorities to processes. The higher the priority, the sooner the process gets served. It's like a VIP lane at a concert. But beware, without proper implementation, it can lead to the starvation of low-priority processes, as they could be left waiting indefinitely. Moving on, we have the round-robin, or RR scheduling algorithm. Each process gets a small unit of CPU time, called a time quantum, and then it's the next process's turn. Think of it as a game of musical chairs where everyone gets a turn. It provides fair scheduling and responsiveness, but may result in high context switch overhead. Next, we delve into the multi-level feedback queue, or MLF queue. This algorithm uses multiple queues with different priorities and scheduling algorithms. Processes move between queues based on their behavior. It's like a multi-lane highway where cars can switch lanes based on speed and destination. It provides a balance between responsiveness and fairness. Last but not least, we have the multi-level feedback queue with aging. It's similar to MLF queue but introduces a concept called aging. It ensures that low-priority processes aren't left waiting forever by gradually increasing their priority over time. It's like an escalator where everyone reaches the top eventually, no matter where they started. As you can see, each scheduling algorithm has its unique advantages and trade-offs, and the choice of algorithm depends on the specific requirements and characteristics of the system and its workload. How does the CPU scheduler decide which process to schedule next? That's where scheduling criteria come in. The scheduler's decision-making process is heavily influenced by 4 key criteria: CPU burst, I/O burst, priority, and age. Let's delve deeper into each one of these. Firstly, there's CPU burst, which refers to the amount of time a process requires to execute on the CPU before it must relinquish control. Processes with shorter CPU bursts are often favored as they can complete quickly and free up the CPU for other tasks. This contributes to a high throughput, or the number of processes completed per unit time. Next up is I/O burst. This is the amount of time a process waits for I/O operations to complete before it can resume execution. Processes with high I/O bursts spend a lot of time waiting, and thus can be moved to the waiting state, freeing up the CPU for other processes. This helps to maximize CPU utilization. The third criterion is priority. This is the relative importance of a process compared to other processes in the system. Higher priority processes are generally scheduled before lower priority ones. This ensures that critical tasks are performed promptly, contributing to a responsive system. Lastly, we have age. This refers to the amount of time a process has spent waiting in the ready queue without being scheduled. Aging is a technique used to prevent indefinite postponement or starvation of low-priority processes. As a process ages, its priority can be gradually increased, ensuring it eventually gets CPU time. This promotes fairness in CPU scheduling. All these criteria are considered by the CPU scheduler in its decision-making process. However, the weightage given to each criterion can vary based on the specific scheduling algorithm in use and the system's requirements. Remember, the goal here is to optimize system performance while ensuring fairness and responsiveness. The scheduler needs to strike a balance between conflicting objectives, such as maximizing CPU utilization and minimizing response time. These criteria provide the CPU scheduler with the necessary information to make informed scheduling decisions and optimize system performance. The final piece of the CPU scheduling puzzle is the dispatcher. This component plays a crucial part in the overall orchestration of process management. The dispatcher is like a traffic controller at a busy intersection, directing the flow of processes in and out of the CPU. Let's dig a bit deeper into the role of the dispatcher. Its primary job is context switching, a task that involves saving the state of a currently executing process and loading the state of the next process in line. By state, we're referring to the vital information about a process, like its memory location and register values. So imagine a process is running on the CPU, and it's now time for it to step aside and let another process have a turn. The dispatcher steps in, saving all the current process's state information. It then loads the state information of the next process to be executed. This transition is a delicate operation and needs to be performed efficiently to maintain system performance. But that's not all. The dispatcher also updates the process control block, or PCB. The PCB is like a process's ID card containing key details like process ID, priority, state, and other scheduling information. As processes move in and out of the CPU, the dispatcher ensures their PCBs are kept up to date. The dispatcher plays a critical role in CPU scheduling, enabling the efficient and seamless transition of control between processes. So there you have it, the ins and outs of CPU scheduling. We've explored the objectives of scheduling, aiming to maximize CPU utilization, minimize turnaround and response times, and ensure fairness. We've dived into a variety of scheduling algorithms, from first come, first served, to multi-level feedback queue with aging, each with its own strengths and weaknesses. We've also examined the criteria used in these decisions, including CPU burst, I/O burst, priority, and age. And let's not forget the crucial role of the dispatcher in context switching and transferring control of the CPU from one process to another. This intricate dance of processes and scheduling is happening right now in the device you're using to watch this video. Remember, CPU scheduling is a fundamental aspect of operating system design, affecting everything from system responsiveness to overall performance. So the next time you use your computer, you'll know there's a sophisticated system working behind the scenes to ensure everything runs smoothly.